What is up, guys? Welcome back to the fourth video on the section about Taylor series. Quick recap of what we learned so far. We defined O(n) of x to be this big, long, nasty looking thing, the integral from a to x of the integral from a to the dummy variable t1, ... all the way to the integral from a to tn of y differentiated m plus 1 times dummy variable tn plus 1, integrated with respect to tn plus 1, and then all the way back to integrated with respect to t2, and then integrated with respect to t1, we learned that if our function y of x, if y is infinitely differentiable on the interval from a to x, where I guess x is not necessarily included in this interval, doesn't have to be differentiable at x, but it has to be differentiable on the whole interval from a to x, a all the way up to x, and all of those derivatives, y differentiated n times, must be continuous on the whole interval from a to x, and that's for all n, so for every nth derivative, and that means all of them. Why is that, though, by the way? Why is it that we need them to be continuous on that whole interval but not necessarily differentiable? Well, just a quick diagram to show what's going on there. So suppose that this is our function, and then this is y of x, and then this is the point x. So here's x, here's y of x. Well, suppose that we're doing all our work kind of, over here integrating, and then all of a sudden the value at y of x is way different to everything else we've been doing. Well, then it's gonna mess everything up because that number is gonna be kind of far away from the others. So yeah, that's why we need it to be continuous. Continuous says that y of x would have to be that point there. So that's what's going on with that. That's why it needs to be continuous on that whole interval, but it only needs to be differentiable up to x, from a up to x. Finally, we also need that the limit as n tends to infinity of O(n) of x must be equal to some number L. In other words, as n gets bigger and bigger, O(n) of x up here should get closer and closer to some other number. O(n) of x should get closer and closer to some other number as n gets bigger and bigger. Okay, if that is the case, then we can write y of x minus L is equal to the Taylor series. The Taylor series is the sum from k equals 0 to, sum from k equals 0 to infinity of y differentiated k times at the point A divided by k factorial times x minus a to the power of k. So that's what we learned last time. Now, what about this number here? What about this number L? Well, does it have to be 0? The answer is actually no. This thing does not necessarily have to be 0. It's kind of a common misconception to think that as long as this series converges, as long as this series gets closer and closer to some number, then it must be equal to the function itself. That's not actually true. This number L does not have to be 0. Let me give you an example of that. So the example is as follows. We got the function y of x is equal to, well, it's kind of split up into two parts. It's going to be e to the negative 1 divided by x squared for x bigger than 0, and it's going to be equal to 0 for x less than or equal to 0. Now, I know it looks like it shouldn't be differentiable everywhere, but it's actually differentiable everywhere. It's continuous and it's differentiable everywhere. As x gets closer and closer to 0, then 1 divided by x squared gets closer and closer to infinity, and e to the negative infinity, I guess, is 0. So actually the whole thing gets closer and closer to 0 as x gets closer and closer to 0, and it's defined as 0 when x is equal to 0. So yeah, this thing is continuous, and it turns out that you can actually differentiate it infinitely many times at 0. So actually for all n, we have that y differentiated n times at the point 0 is equal to 0. To see y, I guess let's do a little bit of work on that. So to see y, let's differentiate it once or twice, I guess. So let's differentiate it once first. Let's take y prime of 0. We know that this is equal to the limit as h tends to 0. Now, first point, we only have to worry about positive h. We know that as h goes to 0 from the negative side, it's always equal to 0. Because for x less than or equal to 0, the whole thing is 0. So we only need to worry about positive h here. So we're only going to be concerned with positive h. So the limit as h tends to 0 of e to the, well, of f of y of h. So the limit as h tends to 0 of y of 0 plus h, which is y of h, which is e to the negative 1 divided by h squared. And it's minus y of 0. Well, y of 0 is 0. So minus 0, and we're dividing that whole thing by h. Well, basically the idea is that as h gets closer and closer to 0, we've got e to the negative 1 over h squared gets closer and closer to 0 than h does. So the thing on the top gets closer and closer to 0 much faster than what h does. The thing on the top gets closer and closer to 0 much faster than h1. So this goes towards 0 faster. And that's important because if the thing on top gets closer and closer to 0 faster, then the whole thing is just going to get closer and closer to 0. Because, if you've got something that's like much smaller on top than the bottom, and it just keeps getting smaller and smaller on top compared to the bottom, then the whole thing is just going to get closer and closer to 0 the more you do that. So this limit is actually equal to 0 when h is positive, and it's equal to 0 when h is negative, and those are the only two directions we can come towards 0 from. So this limit is equal to 0, and y prime of 0 is equal to 0. Okay, so we want to differentiate it again now. We want to differentiate it again. So let's take y prime prime of 0. This is equal to the limit as h tends to 0. Now be careful here. It's you can't just say it's 0 straight away. You got to do a bit more work than that. So this is equal to the limit as h tends to 0 of y prime of 0 plus h, which is just y prime of h, minus y prime of 0, which we just worked out to be 0, divided by h. Now, we need to be concerned with h greater than 0, because once again, for h smaller than 0, everything's just defined to be 0. We can clearly see that y prime of anything less than 0 needs to be 0, because the whole thing is 0 for x less than or equal to 0. So h needs to be bigger than 0. Well, when h is bigger than 0, let me use a different color. When h is bigger than 0, y of h is equal to e to the negative 1 divided by h squared. And therefore, y prime of h, we can actually just differentiate using the chain rule. So differentiate negative 1 over h squared. You can check me on this, that it's 1 divided by h cubed. And then, well, e to the power of anything differentiated by itself is still e. So you multiply those together. E to the negative 1 divided by h squared. So that's y prime of h. And so basically y prime of h divided by h is this thing divided by h. And so it's actually equals, I'm out of room. Let me continue on the next page. Equals limit as h tends to 0 of e to the negative 1 divided by h squared divided by h to the power of 4. And once again, this one goes to 0 much faster than this one. The top one goes to 0 much faster than the bottom one as h gets smaller and smaller. Think about e to the power of even, e to the power of 20. Think about how huge that is. E times e times e. It's going to get really, really big compared to the one on the bottom. Sorry, going to get really, really small compared to the one on the bottom. The one on the bottom is also getting closer and closer to 0, but it's compared to the one on the top, it's not going there very quickly at all. So the whole thing gets closer and closer to 0, and so the limit is equal to 0, and remember this limit was equal to y prime prime of 0. And you can show that it's true using something called induction, or basically just common sense, by showing that if you do it for any n, you're basically going to end up with, for any n, let me write this down, for any n, you're going to basically have y prime prime, y differentiated n times at the point 0 is going to be equal to some polynomial p1, it's going to be equal to the limit as h tends to 0 of some polynomial p1 of h divided by another polynomial p2 of h times e to the negative 1 over h squared. And as always, e to the negative 1 over h squared is going to go to 0 so much quicker than the thing on the bottom that the whole thing is just going to go to 0. So it's true. For every n, when we differentiate this function n times at the point 0, the answer is 0. Okay, so that was a big, long ramble off topic. Kind of off topic. Let me use this board. I'll make a new board. So what we've got here is the function y of x is equal to e to the negative 1 over x squared for x greater than 0, and it's equal to 0 for x less than or equal to 0, and we have that y differentiated n times at the point 0 is equal to 0 for all n. Well, can anyone see the problem? Okay, well, the problem is as follows. When we write out the Taylor series, 6 will do. When we write out the Taylor series, we have that y of x minus L is equal to the sum from k equals 0 to infinity of y differentiated k times at the point 0 divided by k factorial times x minus 0 to the power of k, so that's times x to the power of k. Well, what we just showed is that actually for all k values, y differentiated k times at 0 is equal to 0, and so this whole thing is equal to 0. So according to this, y of x minus L is equal to 0. But y of x does not equal 0 for any x bigger than 0. Remember, this function here, y of x, is differentiable everywhere. And so it's going to be differentiable from 0 to any value of x that we want. And so all of our theorems, all of our theory from before will apply to this function. And hence, this y of x, well, we can put positive values of x into it as well if we want to. We should be able to put positive values of x into here. And we know for sure that, say, x equals 5. Then we have that y of 5 minus L equals 0. And in other words, well, actually, L, can't really write that, can I? L is defined, so I'm going to call this L of 5. L depends on the x value that you put into it. So y of 5 minus L of 5 equals 0. And in other words, L of 5 is equal to e to the negative 1 over 25, e to the negative 1 over 5 squared. So this L depends on x, by the way, in case, yeah, I didn't really make that clear before, did I? That L depends on the value of x. And in fact, for general x, we can see now that L of x is going to be equal to e to the negative 1 over x squared if x is bigger than 0, and it's going to be equal to 0 if x is less than or equal to 0. So in fact, L of x is equal to y of x, which I now see is exactly what I had written here anyway. Okay, so that's an example of where L doesn't necessarily have to be 0. So if we go back to what we were writing before, for this Taylor series, this thing not always 0 if Taylor series converges. Not always 0 if Taylor series converges. So just because this thing on the right-hand side converges doesn't mean it necessarily has to be equal to y of x. They don't necessarily have to be equal to each other. Okay, that's all for this part. Thank you very much for watching. Don't forget to check out the notes and do the exercises, and I'll see you in the next bit. Thanks very much. Take care. Bye.